Hello, my name is Matt Bergdahl, and I'm here with Team 17 for our final presentation movie on our pizza dough factory project. So the goal of our pizza dough factory is to produce 2,400 pre-portioned pizza dough balls to be delivered to local pizza chain, in our case Buddy's, within Oakland County, with the goal of minimizing the overall cost per day of the manufacturing and distribution. Minimizing this cost enables Buddy's Pizza to maximize their profits while maintaining a good product. So for our subsystem overview, we have our first subsystem, one, which is our dough mixing. Here we see our dough mixer, which is pretty much fed with the optimal amounts of the ingredients needed to make the dough. And then in subsystem two, we have the portioning and packing into dough bins. We can see the robot arm on the right moving the dough balls off of the conveyor belt and over to the left into the box. Next, we have the dough bin transportation logistics. We can see there a guy loading up the truck to be distributed to our restaurants. Next, we have the system flow diagram. So the main thing here is our number of stores is our kind of lead blocker here. The number of stores produce the demand for the dough balls, and then the factory is up to produce and distribute the dough balls. The other thing to note here is that we have electricity built into the first two subsystems as they are doing the bulk of the manufacturing of the product. And finally, all three of the subsystems lead to a cost, which in the end, our goal is to try to minimize. Next, I'll kick it over to Ala for optimization system model.
Thanks, Matt. And now moving to the system optimization model. We've listed the parameters of the systems, including those related to the dough ball ingredients, those related to the robot mixer, and those related to transportation along the determined route. We've also outlined the design and intermediate variables to the left, as well as the constraints on the right. It's worth mentioning that the design variables outlined in this problem are local to each subsystem, since there are no shared variables between the subsystems. Combining all the objective functions from the three subsystems for full system optimization, we obtain the objective function of the system, which focuses on optimizing the total daily cost, which includes the cost of ingredients, the cost of the mixing, the cost of power, and the delivery cost. The trade-offs between the constraints and the objective function are shown to the right, where the increase in ingredients leads to increased dough balls and bins, which ultimately leads to increased delivery time, which could risk surpassing the freshness window constraint. Therefore, trade-offs need to be monitored to remain within allowed limits. We've also demonstrated the optimization model in the negative null form, in which we'd be maximizing the negative of the total daily cost, and the constraints would be formatted as shown, with constraints shown as less than or equal to 0, and ensuring that physical entities are greater than or equal to 0. And now I'll hand it off to Jamie.
As a final note on the optimization model, we look at the linked variables between subsystems. Subsystem 1 and 2 share the cost of energy as an initial parameter, as well as demand or number of dough balls produced. While this demand depends on the number of stores considered in subsystem 3, there is no other direct link between the three subsystems. Therefore, we see that our optimized solution for our combined systems is equal to the sum of the individual optimized solutions.
Now I will go over our system's mathematical modeling. For the assumptions we made during our mathematical modeling, our first assumption is the system goal is to minimize the cost per day of pizza dough production. The system daily output is constant. Ingredient, power, and fuel costs are fixed. Min power occurs when both flour and oil amounts are at the minimum. Power output is based on dry and wet ingredient ratios. Total mass of wet and dry ingredients is fixed. Min power output to mix the dough is 5 kilowatts. Speeds for extrusion, tumbler, and robot placement are linearly related to cycle time. There is no downtime and environmental conditions. 8 pizza store locations in Oakland County area with the pizza dough warehouse located in Pontiac. The average speed of the delivery driver is 30 miles per hour, and the unloading time is 5 minutes. Here are our system level equations. First is ingredient cost, which will consist of the cost and weight of each ingredient, the mixing dough cost, which will consist of those ingredient ratios and electricity cost, the cycle time of our extruder, which will include the volume, surface area, and extrusion velocity, the cycle time of the tumbler, which will include variables such as the surface area of the dough, roller circumference, and tumbler velocity, and the cycle time of the placement, which will include the Euclidean distance of the robot and robot velocity. Here are equations continued for the total cycle time. This will include the cycle time of the extruder, tumbler, and placement time. For our total power cost, the variables will include total cycle time, daily demand, energy cost, and average daily power. For our total delivery time, we'll be using a distance matrix used during the map that was created, the average speed, and the number of stores and unloading time. And this will allow us to calculate the total delivery cost, which will be the fuel cost times the total distance. This will allow us to create our objective function, which is going to be our ingredient costs, mixing costs, power costs, and delivery costs together. For this, we are using an optimization. Our optimization method will be using MATLAB, and in MATLAB, we'll be using a constrained nonlinear programming problem using MATLAB's FimCon section. This function was selected because it's ideal for the task, as it efficiently minimizes a nonlinear multivariable function while handling equality and inequality constraints.
Thanks, Andrew. Next, I'll go over the optimization results. So for our optimization results, the code was ran 5 times with various initial conditions and parameters, and it was found that the objective function value and also the design values did not vary throughout each of the tests. These results suggest that our code and our FminCon optimization algorithm is very robust and that our feasible region is very well behaved. The total cost per day, which is our objective function goal, was found to be $2,975.30 per day, with our optimal amounts of ingredients and the robot speeds shown above in the table. And as you can see, just glancing at the table, the values did not change through each run. And now I'll kick it over to Madeline for our post-optimality sensitivity analysis.
Thanks, Matt. Now I'll review the post-optimality sensitivity analysis. Here's an overview of the constraints we performed the sensitivity analysis on. We did not include the constraints limiting duplicate visits or restricting the routes because these were binary and not very negotiable. After perturbing the constraints up and down, we found that the lower bound on oil weight had the highest impact on the final F-star value. This impact was compared and quantified using percent difference from the original system F-star. At the bottom, you can see a strip plot of all of the results, showing that the lower bound of the oil weight had the highest percent difference. Because our system had more than 3 parameters, only 3 were chosen for this analysis. These were cost per gram of oil, because the oil weight constraint was one of the highest impacts, the cost of fuel per mile, because gas prices are always changing, and bin demand, because this just made sense that it would affect our overall production costs. And as you can see, the bin demand did have the highest percent difference when we modified it into the negative direction, as well as in the positive direction. Next, I will hand it off to Brooke and Jamie to discuss our results. Thank you.
Now, onto our discussion of results with myself, Brooke, and Jamie. We assessed key variables to ensure that our system was aligned with reality. On the left, the FDC validated our optimized ingredient ratio. Our dough ratio was 34% water and 1% salt, which closely matches the FDC values for commercially prepared whole wheat bread, demonstrating a comparable formula. In the middle, the Grote pizza machine validated our dough process cycle time. Our system achieved 60 pizzas per minute per lane, which slightly outperformed Grote's 45 pizzas. The slight delta can be explained by our system not including a sauce or toppings area, allowing us to output more pizzas. On the right, MapQuest validated our miles driven. Our system traveled 87 miles across 8 locations. Compared to MapQuest's estimate of 80 miles, the 7-mile difference is likely due to the highway route variations versus the linear distance assumption for our system.
We now compare the subsystems to our total system. We can see the difference between summing up our individual subsystem solutions results in $2,975.10 a day, while our optimized total solution is $2,975.30 a day. This difference of 20 cents is likely attributed to rounding error, telling us that our combined solution aligns well with the sum of individual solutions. This follows our expectations due to the lack of linked variables between systems, as discussed earlier. Now, back to Brooke.
To conclude, our engineering analysis shows the system's objective function aligns with real-world applications and achieves the objective function goal. Our system's daily cost aligns closely with the sum of the subsystem costs, suggesting minimal interdependence of subsystems, meaning we can further optimize subsystems with minimal impact on other subsystems. Future work to improve model fidelity includes increasing the number of production lines and delivery trucks to better reflect large-scale operations. Additionally, we plan to expand the system boundaries to include labor costs across subsystems, improving efficiency of labor wage allocation. We will also allow for varying demand requests to strengthen inner subsystem constraints and identify potential bottlenecks. Thank you.